Okay, so last time we came across a new idea, although it wasn't really new for a lot of you, and that was the idea of Nash equilibrium. And what I want to do today is discuss Nash equilibrium, see how we find Nash equilibrium in some rather simple examples, and then in the second half of today, I want to look at an application where we actually have some fun and play a game, at least I hope it's fun. All right, but let's start by putting down a formal definition. We only used a rather informal one last week, so here's a formal one. A strategy profile, remember a profile is one strategy for each player, so it's going to be S1 star, S2 star, all the way up to Sn star if there are n players playing the game. So this profile is a Nash equilibrium, and I'm just going to write Ne in this class for Nash equilibrium from now on. If for each I, so for each player I, her choice, so her choice here is Si star, that's I's part of that profile, is a best response, to the other player's choices, And of course, the other player's choices here are S minus I star. So everyone is playing a best response to everyone else. All right? Now, this is by far the most commonly used solution concept in game theory. So those of you who are interviewing for McKinsey or something, you're going to find that they're going to expect you to know what this is. All right? So one reason for knowing what it is because it's in the textbooks, it's going to be used in lots of applications, it's going to be used in your McKinsey interview. That's not a very good reason, right? And I certainly don't want you to jump to the conclusion that now we've got to Nash equilibrium, everything we've done up to now is somehow, in some sense irrelevant. That's not the case. It's not always going to be the case that people always play a Nash equilibrium. For example, when we played the numbers game, the game when you chose a number, we've already discussed last week, or last time, that the equilibrium in that game is for everyone to choose 1. But when we actually played the game, the average was much higher than that. The average was about 13. It is true that when we played it repeatedly, it seemed to converge towards 1. But the play of the game when we played it just one shot, first time, wasn't a Nash equilibrium. Right? So we shouldn't fall into the mistake of thinking people always play Nash equilibrium, or people, if they're rational, play Nash equilibrium. Neither of those statements are true. Nevertheless, there are some good reasons for thinking about Nash equilibrium other than the fact it's used by other people, and let's talk about those a bit. So I want to put down some motivations here. All right, the first motivation we already discussed last time. In fact, somebody in the audience mentioned it, and it's the idea of no regrets. So what is this idea? It says, suppose we're looking at a Nash equilibrium. If we hold the strategies of everyone else fixed, no individual I has an incentive to deviate, to move away. All right, so again, holding everyone else's actions fixed, no individual has any incentive to move away. And let me be a little bit more careful here. No individual has any strict incentive to move away. All right, we'll see that that actually matters. Right, so no individual can do strictly better by moving away. All right? No individual can do strictly better by deviating, comma, holding everyone else fixed. All right? So why do I call that no regret? It means having played the game, suppose you did in fact play a Nash equilibrium, and then you look back at what you've done, and now you know what everyone else has done, and you say, do I regret my actions? And the answer is, no, I don't regret my actions, because I did the best I could given what they did. All right? So that seems like a fairly important sort of central idea for why we should care about Nash equilibrium. Here's a second idea, and we'll see others arise in the course of today. A second idea is that a Nash equilibrium can be thought of as self-fulfilling beliefs. So in the last week or so, we've talked a fair amount about beliefs. If I believe the goalkeeper is going to dive this way, I should shoot that way, and so on. All right? But of course, we didn't talk about any beliefs in particular. These beliefs, if I believe that, if everyone in the game believes that everyone else is going to play their part of a particular Nash equilibrium, then everyone will in fact play their part of that Nash equilibrium. All right? Now why? Why? Why is it the case that if everyone believes that everyone else is playing their part of this particular Nash equilibrium, that that's self-fulfilling and people actually will play that way? Why is that the case? Anybody? Yeah, can we get this guy in red? Yeah?
Because your own Nash equilibrium strategy is the best response against those.
Exactly, exactly. So it's almost a repeat of the first thing. If I think everyone else is going to play their particular, if I think players 2 through n are going to play S2 star through Sn star, then by definition, my best response is to play S1 star, so I will in fact play my part of the Nash equilibrium. All right, good, good. All right, so as part of the definition, we can see these are self-fulfilling beliefs. Let's just remind ourselves how that arose in the example we looked at the end last time. I'm not going to go back and reanalyze it, but I just want to sort of make sure that we followed it. So we had this picture last time in the partnership game in which people were choosing effort levels. And this line was the best response for player 1 as a function of player 2's choice, and this line was the best response of player 2 as a function of player 1's choice. All right, this was the picture we saw last time. And let's just look at how those, it's no secret here what the Nash equilibrium is. The Nash equilibrium is where the lines cross, but let's just see how it maps up to those two motivations we just said. So how about self-fulfilling beliefs? Well, if player, sorry, I've put a 1, that should be 2. If player 1 believes that player 2 is going to choose this strategy, then player 1 should choose this strategy. If player 1 thinks player 2 is choosing this strategy, then player 1 should choose this strategy. If player 1 thinks player 2 is choosing this strategy, then player 1 should choose this strategy, and so on. That's what it means to be a best response. But if player 1 thinks that player 2 is playing exactly her Nash strategy, then player 1's best response is to respond by playing his Nash strategy. And conversely, if player 2 thinks player 1 is playing his Nash strategy, then player 2's best response, indeed, is to play her Nash strategy. All right, so you can see that's a self-fulfilling belief. If both people think that's what's going to happen, that is indeed what's going to happen. All right, how about the idea of no regrets? So here's player 1, she wakes up the next morning, oh sorry, it was he, wasn't it? He wakes up the next morning and he says, I chose S1 star, do I regret this? Well, now he knows what player 2 chose S2 star, and he says, no, that's the best I could have done. Given that player 2 did in fact choose S2 star, I have no regrets about choosing S1 star. That in fact was my best response. And notice that wouldn't be true at some other outcome. So for example, if player 1 had chosen S1 star, but player 2 had chosen some other strategy, let's say S2 prime, then player 1 would have regrets. Right? Player 1 would wake up the next morning and say, oh, I thought player 1 was going to play S2 star. In fact, she chose S2 prime. I regret having chosen S1 star. I would have rather chosen S1 prime. Right? So only at the Nash equilibrium are there no regrets. Right? Everyone okay with that? This is just revisiting really what we did last time and underlining these points. All right. So I want to spend quite a lot of time today just getting used to the idea of Nash equilibrium and trying to find Nash equilibrium. I'm going to turn off that projector that's in the way there, if I can. There we go. Is that going to upset the lights a lot? All right. So, okay. So what I want to do is I want to look at some very simple games with a small number of players to start with and a small number of strategies, and I want us to get used to how we would find the Nash equilibria in those simple games. Okay? We'll start slowly, and then we'll get a little faster. Okay, so let's start with this game. Very simple game with 2 players. Each player has 3 strategies, and I'm not going to motivate this game, it's just some random game. Player 1 can choose up, middle, or down, and player 2 can choose left, center, and right, and the payoffs are as follows: 0-4, 4-0, 5-3, 4-0, 0, 4, 5, 3 again, 3, 5, 3, 5, and 6, 6. All right? So we could discuss, if we had more time, we could actually play this game, but it isn't a particularly exciting game, so let's leave our playing for later. And instead, let's try and figure out what are the Nash equilibria in this game and how we're going to go about finding them. Right? And the way we're going to go out finding them is going to mimic what we did last time. Last time, we had a more complicated game in which there was 2 players with a continuum of strategies, and what we did was we figured out player 1's best responses and player 2's best responses, player 1's best response to what player 2's doing, and player 2's best response to what player 1's doing, and then we looked where they coincided, and that was the Nash equilibrium. And we're going to do exactly the same in this simple game here. So we're going to start off by figuring out what player 1's best response looks like. All right? So in particular, what would be player 1's best response if player 2 chooses left? What would be player 1's best response if player 2 chooses left? Let's get the mics up so I can sort of challenge people. Anybody? Not such a hard question. Do you want to try the woman in the middle? Who's closer to the woman in the middle? Yeah.
Middle, M.
Okay, so player 1's best response in this case is middle, all right, because 4 is bigger than 0 and is bigger than 3, all right? So to mark that fact, what we can do is let's put a circle, if you like in green, let's put a circle round that 4. Okay? All right, not hard, right? So let's do it again. What is player 1's best response if player 2 chooses center? What is player 1's best response if player 2 chooses center? Let's get somebody on the other side. Somebody, you should feel free to cold call somebody here. So how about cold calling the guy with the Yale football shirt on? Here we go.
Up.
All right, so up is the correct answer. All right, so that's one triumph for Yale football. Okay, so all right, so 4 is bigger than 3, bigger than 0. All right, so good. Thank you. All right, and Ali, why don't you do the same? Why don't you cold call somebody who's going to tell me what's the best response for player 1 to right?
Down.
Shout it out.
Down.
Down. Okay. Okay. So best response is down because 6 is bigger than 5, which is bigger than 5. I mean, 6 is bigger than 5. Okay. All right. All right. So what we've done here is we've found player 1's best response to left, best response to center, and best response to right. And in passing, notice that each of player 1's strategies is a best response to something. So nothing would be knocked out by our domination arguments here, and nothing would be knocked out by our never a best response arguments here for player 1. Okay? Okay? Let's do the same for player 2. So why don't I keep the mics doing some cold calling? So do you want to cold call somebody at the back to tell me what is player 2's best response against up? What's player 2's best response against up? I'm struggling on that.
Yeah, left.
All right, so the gentleman in blue says left because 4 is bigger than 3 is bigger than 0. Let's switch colors and switch polygons and put squares around these, okay? Right. I don't insist on the circles and the squares. If you have a thing for hexagons, you can do that too, right? Whatever you want. All right. All right, what's player 2's, so let's write it in here, the answers. The answer was that the best response was left, all right? And player 2's best response to middle, so Merton, do you want to grab somebody over there?
Center.
Shout it out.
Center.
All right, because 4 is bigger than 3, which is bigger than 0, so that's center. And in my color coding, that gives me a square here. And finally, player 2's best response to down, and your turn, Ali. Let's grab somebody.
Is left. I'm sorry, right.
Okay, right. Okay, good, because 6 is bigger than 5 again. Okay, so here we go. All right. So what we've done now is found player 1's best response function. That was just the analog of finding the best response line we did here. Here we drew it as a straight line in white, but we could have drawn it as a sequence of little circles in green. It would have looked like this, right? The same idea. We're not going to do the whole thing, right? It would be a whole bunch of circles looking like this. And then we found player 2's best response for each choice of player 1, and we used pink rectangles, and that's the same idea as we did over here. Here we did it in a continuum strategy using calculus, but it's the same idea. So imagine I'm drawing lots of pink rectangles, and again, I'm not going to do it, but you can do it in your notes, okay? All right, same basic idea. And just as the Nash equilibrium must be where these best response lines coincided here, because that's the point at which each player is playing a best response to each other, all right? So the Nash equilibrium over here is, drum roll, do you want to cold call somebody? Do you want to cold, just grab somebody in the row behind you or something, whatever? Yeah? Anybody? All right. Yeah, I think you were in Italia soccer shirt. You're going to get picked on. So okay. So what's the Nash equilibrium here?
The bottom right square.
All right. So the down right square. So the Nash equilibrium here is no prizes, no World Cup for that one. Is down right. All right. All right. So why is that the Nash equilibrium? Because at that point, player 1 is playing a best response to player 2, and player 2 is playing a best response to player 1. Right? Now I want to try and convince you, particularly those of you who are worried by the homework assignment, that that was not rocket science. Right? Right? It's not hard to find Nash equilibria in games. All right? Well, it didn't take us very long, and we went pretty slow, actually. All right. So let's look at another example. Oh, before I do, notice that before I leave this game, let's make one other remark. Notice that in this game that each strategy of player 1 is a best response to something, and each strategy of player 2 is a best response to something. So had we used the methods of the earlier on in the class, that's to say deleting dominated strategies, or deleting strategies that are never a best response, we'd have got nowhere in this game. All right? All right? So Nash equilibrium has got us a little further in narrowing down our predictions. But we also learned something from that. We argued last time and in the last few weeks that rationality, or even mutual knowledge of rationality, or even common knowledge of rationality, couldn't really get us much further than deleting dominated strategies, or if you like, deleting strategies that are never best responses. All right? So here we've concluded that the Nash equilibrium of this game is downright, a very particular prediction. But notice, a perfectly rational player could choose middle. The reason they could choose middle, player 1 could choose middle, could be that if they say rationally they should choose middle because they think player 2 is choosing left. And you say, well, why would you think player 2 is going to choose left? And player 1 could say, I think player 2 is going to choose left because player 2 thinks I'm going to play up. And then you say, but how could player 2 possibly think that you're going to play up? And then player 1 would say, I think player 2 thinks I'm going to play up because player 2 thinks that I think that he's going to play center. And then you could say, how could player 2, et cetera, et cetera, et cetera. And you can see you could work yourself around a little cycle there. Nobody would be irrational about anything. Everything would be perfectly well justified in terms of beliefs. It's just we wouldn't have a nice fixed point. We wouldn't have a nice point where it's a simple argument. In the case of down right, player 1 thinks it's OK to play down because he thinks 2 is going to play right. And player 2 thinks it's OK to play right because he thinks player 1 is going to play down. Right? So just to underline what I'm saying rather messily there, rationality and those kind of arguments should not lead us to the conclusion that people necessarily play Nash equilibrium. All right? We need a little bit more. We need a little bit more than that. Nevertheless, we are going to focus on Nash equilibrium in the course. All right, let's have a look at another example. And again, we'll keep it simple for now, and we'll keep to a 2-player, 3-strategy game. Up, middle, down, left, center, right. And this time the payoffs are as follows. 0-2, 2-3, 4-3, 11-1, 3-2, 0-0, 0-3, 1-0, and 8-0. So this is a slightly messier game. The numbers were really just whatever came into my head when I was writing it down. And once again, we want to find out what the Nash equilibrium is in this game. And our method is exactly the same. We're going to for each player, figure out their best responses for each possible choice of the other player. So rather than write it out in 4, let me just go straight to my green circles and red squares, and let me get my mics up again, all right, so we can cold call people a bit. All right, can we get the, where's the mic? Oh, thank you, thank you. All right, so Ali, do you want to just grab somebody and ask them what's the best response against left? You can grab anybody, doesn't it? What's the best response against left?
Middle.
Middle, okay, good, good. So middle is the best response against left because 11 is bigger than 0. All right, Merton, you want to grab somebody? What's the best response against center?
Middle.
Middle again, because 3 is bigger than 2 is bigger than 1. And grab somebody at the back and tell me what the best response is against right. Anybody? Anybody? Just dive in. Yep.
Down.
Okay, down, good. All right, and let's do the same for the column player. So what's the column player's Ali, find somebody, take the guy who's 2 rows behind you who's about to fall asleep and ask him, what's the best response to up?
The best response would be for which player?
For player 2. So what's player 2's best response for up? Sorry,
I'm going to
pick on someone else. That's right. Pick on the guy right behind you. Okay. What's the best response for up?
C and R are tied. So C or R.
All right. So this is a slightly more tricky one, right? The best response to up is either C or R. This is why we got you to sign those legal forms, right? Okay. Best response to up is either C or R. The best response to middle, yeah, madam?
Center.
Is center, thank you. And the best response to down?
Left.
All right, so the best response to down is left. And here again, it didn't take us very long. We're getting quicker at this. The Nash equilibrium in this case is the Nash equilibrium. Let's go back to the guy who is asleep and give him an easier question this time. So the Nash equilibrium in this case is?
Nash equilibrium would be the 3-2 combination?
Exactly. Okay, so the middle center. All right? And notice this is a Nash equilibrium. Why is it a Nash equilibrium? Because each player is playing a best response to each other. Right? If I'm player 1 and I think that player 2 is playing center, I should play middle. If I'm player 2, I think player 1 is playing middle, I should play center. If, in fact, we play this way, neither person has any regrets. Notice they didn't do particularly well in this game. In particular, player 1 would have liked to get this 11 and this 8. Right? But they don't regret their action because given that player 2 played center, the best they could have got was 3, which they got by playing middle. Right? Notice in passing in this game, that best responses needn't be unique. Right? Sometimes there can be a tie in your best response. Okay? That can happen. All right, so what have we seen? We've seen how to find Nash equilibrium, and clearly it's very closely related to the idea of best response, which is an idea we've been developing over the last week or so. All right, but let's go back earlier in the course and ask, how does it relate to the idea of dominance? Right? This is really our third concept in this course. Right? We had a concept about dominance, we had a concept about best response, and now we're at Nash equilibrium. It's, I think, obvious how it relates to best response. It's when best responses coincide. How about how it relates to dominance? Well, to do that, let's go back. So what we're going to do is we're going to relate Nash equilibrium to our idea of dominance, or of domination. All right? And to do that, an obvious place to start is to go back to a game that we've seen before. So here's a game where player 1 and player 2 are choosing alpha and beta, and the payoffs are 0, 0, 3, minus 1, minus 1, 3, and 1, 1. All right, so this is the game we saw the first time. This is the prisoner's dilemma. All right, and we know in this game, I'm not going to bother to cold call people for it, we know in this game that beta is dominated, is strictly dominated by alpha. All right, so we learned the very first time. All right, just to check. All right, so against alpha, choosing alpha gets you 0, beta gets you -1. Against beta, choosing alpha gets you 3, beta gets you 1. In either case, alpha is strictly better, so alpha strictly dominates beta. And of course, it's the same for the column player, since the game's completely symmetric. All right? So now let's find the Nash equilibrium in this game. I think we know what it's going to be, all right? But let's just do it in a sort of slow way, all right? So the best response to alpha must be alpha. The best response to beta must be alpha. And for the column player, the best response to alpha, I was doing it in pink, wasn't I? The best response to alpha must be alpha. And the best response to beta must be alpha. Everyone okay with that? I'm rushing it a bit because it's kind of obvious. Is that right? Okay. And so the Nash equilibrium in this game, the Nash equilibrium is alpha alpha. In other words, it's what we would have arrived at had we just deleted strictly dominated strategies. Right, so here's a case where alpha strictly dominates beta, and sure enough, Nash equilibrium coincides. It gives us the same answer. Both people choose alpha in this game. All right, so there's no news here. I'm just checking that we're not getting anything weird going on. All right, so let's just be a bit more careful. All right, how do we know it's the case? So I'm going to claim it's the case that no strictly dominated strategy, in this case beta, no strictly dominated strategy could ever be played in a Nash equilibrium. So I claim that's a good thing, right? Because we want these ideas to coincide. I claim that no strictly dominated strategy could ever be played in a Nash equilibrium. Why is that the case? Yeah, there's a guy up here, yeah?
A strictly dominated strategy isn't the best response to anything, so
Good.
It couldn't be the best response to their playing the Nash equilibrium.
Good, very good. So a strictly dominated strategy is never a best response to anything. In particular, the thing that dominates it always does better. All right? So in particular, it can't be a best response to the thing being played in Nash equilibrium. All right? So that's actually a very good proof. That proves that no strictly dominated strategy could ever be played in a Nash equilibrium. But now we have, unfortunately, a little wrinkle. And the wrinkle, unfortunately, is weakly dominated, is weak domination. So we've argued, in fact it was fairly easy to argue, that no strictly dominated strategy is ever going to reappear, annoyingly, in a Nash equilibrium. But unfortunately, the same is not true about weakly dominated strategies. And in some sense, you had a foreshadowing of this problem a little bit on the homework assignment, where you saw, one of the problems, I think it was the second problem on the homework assignment, that deleting weakly dominated strategies can lead you to do things that might make you feel a little bit uneasy. All right? So weak domination is really not such a secure notion as strict domination, and we'll see here a trivial example of that in a game. So here's a trivial example, not an interesting example, but it just makes the point. So here's a 2x2 game. Player 1 can choose up or down, and player 2 can choose left or right. And the payoffs are really trivial. 1, 1, 0, 0, 0, 0, 0, 0. All right? So let's figure out what the Nash equilibrium is in this game, and I'm not going to bother cold calling because it's too easy. So the best response for player 1, if player 2 plays left, is clearly to choose up. And the best response of player 1, if player 2 chooses right, is, well, either up or down will do, right? Because either way he gets or she gets 0. So these are both best responses. Is that correct? They're both best responses. They both do equally well. All right? And conversely, player 2's best response, if player 1 chooses up, is sure enough to choose left. And that's kind of the answer we'd like to have. But unfortunately, when player 1 plays down, player 2's best response is either left or right. It makes no difference. They get 0 either way. All right? Okay. So what are the Nash equilibria in this game? What are the Nash equilibria in this game? So notice first observation is there's more than one Nash equilibrium in this game. Right? We haven't seen that before. All right? There's a Nash equilibrium with everybody in the room, I hope, thinks is kind of the sensible prediction in this game. Right? In this game, I think all of you, I hope, if you're player 1 would choose up, and all of you for player 2 would choose left. Is that right? Is that correct? Right, it's hard to imagine coming up with an argument that wouldn't lead you to choose up and left in this game. All right? However, unfortunately, this isn't unfortunate. Up left is a Nash equilibrium, but so is down right. Right? If player 2 is choosing right, your best response, weakly, is to choose down. If player 1 is choosing down, player 2's best response, weakly, is to choose right. All right? And this is arriving because of the definition of Nash. It's a very definite definition. When we looked at the, I've deleted it now, never mind. When we looked at the definition, we said something is a Nash equilibrium if each person is playing a best response to each other. Another way of saying that is no player has a strict incentive to deviate. No player can do strictly better by moving away. So here at down right, player 1 doesn't do strictly better, it's just a tie if she moves away. And player 2 doesn't do strictly better if he moves away, it's a tie, he gets 0 either way. So here we have something which is going to worry us going on in the course. Sometimes we're getting, not only are we getting many Nash equilibria, that's something which shouldn't worry us, it's a fact of life, but in this case, one of the Nash equilibria seems silly, right? I mean, if you went and tried to explain to your roommates and said, you know, I predict both of these outcomes in this game, they'd laugh at you. It's obvious in some sense that this has to be the sensible prediction. All right? So just a sort of worrying note before we move on. Okay, so this was pretty formal and kind of not very exciting so far. So let's try and move on to something a little bit more fun. Okay, so what I want to do now is I want to look at a different game. Again, we're going to try and find Nash equilibria in this game, but we're going to do more than that. We're going to talk about the game a bit. And a feature of this game, which is to distinguish it from what we've done so far, is the game we're about to look at involves many players, although each player only has few strategies. All right, so what I want to do is I want to convince you how to find, I want to discuss how to find Nash equilibria in a game which, unlike these games, doesn't just have 2 players, it has many players, but fortunately not many strategies per player. All right? So let me use this board. All right? So this is going to be called the investment game. And we're going to play this game, although not for real. All right, so the players in this game, as I've just suggested, the players are going to be you. All right, so everyone who was getting sleepy just looking at this kind of analysis should wake up now. You have to play. All right, and the strategies in this game are very simple, the strategy sets, or the strategy alternatives. Each of you can choose between investing nothing in a class project, 0, or invest $10. All right? So I'm sometimes going to refer to investing nothing as not investing. Is that okay? Right? It seems like a natural thing. So you're either going to invest $10 or nothing, i.e. you're not going to invest. All right? So that's the players, and those are the strategies. So as usual, we're missing something. What we're missing are the payoffs. All right, so here are the payoffs. So the payoffs are as follows. If you don't invest, if you do not invest, i.e. you invest nothing, then your payoff is 0. All right, so nothing ventured, nothing gained. Right, natural thing. All right, but if you do invest, you invest $10, remember each of you is going to be investing $10, then your individual payoffs are as follows. Here's the good news. You're going to get a profit of $5. The way this is going to work is you're going to have invested $10, so you'll make a gross profit of 15 minus the 10 you originally invested for a net of 5. Everyone understand, right? So a net profit, so $5 net profit. That's the good news, but that requires more than 90% of the class to invest. Greater than or equal to 90% of the class to invest. If more than 90% of the class invest, you're going to make essentially 50% profit. And unfortunately, the bad news is you're going to lose your $10, get nothing back, right? So this is a net loss if fewer than 90% of the class invest. All right, I mean, the key rule here, you're not allowed to talk to each other. Right? No communication in the class, no hand signals, no secret winks, right? Nothing else, all right? Okay? So everyone understand the game, including up on the balcony. Everyone understand the game? All right? So what I want you to do, I should say, first of all, we can't play this game for real because there's something like 250 in you, and I don't have that kind of cash lying around. Right? So pretend we're playing this for real, okay? Pretend we're playing this for real. Right? So without communicating, I want each of you to write on the corner of your notepad whether you're going to invest or not. So you can write Y if you're going to invest, and N if you're not going to invest. Don't discuss it with each other, just write down on the corner of your notepad Y if you're going to invest, and N if you're not going to invest. Don't discuss it, guys. Don't discuss it. All right, and now show your neighbor what you did, just so you can your neighbor can make you honest. All right. Now, okay, let's have a show of hands. All right. So what I want to do is I want to have a show of hands. Everybody who invested. Everyone who invested. Don't look around. Just raise your hands. Everyone who invested and everyone who didn't invest. Oh, that's more than 10%. All right, let's do that again. So everyone who invested, raise their hands. Raise their hands. And everyone who didn't invest, raise their hands. So I don't know what that is. Maybe it's about half. About half. So now I'm thinking we should have played this game for real. I want to just get some discussion going about this. Right? I'm quite willing to discuss this for a while. There's a lot to be said about this game. Let me borrow that. Can I borrow this? All right. So this guy. OK, so what did you do?
I invested.
Why did you invest?
Because I think I can lose $10.
All right. So he's rich. That's OK. It's OK. You can pay for lunch. That's all right. That's all right. All right. Who didn't invest? Non-investors. Yeah. So here's one. So OK. So why didn't you invest? Shout it out so everyone can hear.
I didn't invest because to make a profit, there needs to be at least a 2-to-1 chance that everyone else, that 90% invests.
All right. You mean to make an expected profit?
Yeah, you only get half back, but you lose the whole thing.
I see. OK. So you're doing some kind of expected calculation. Other reasons? Other reasons out there? What did you do?
I invested.
You invested. We have to, I'm finding the suckers in the room. OK, so you invested. And why?
Because you stand to gain something. I don't see why anybody would just not invest, because they would never gain anything.
All right. So your name is?
Clayton.
So Clayton's saying, only by investing can I gain something here. Not investing seems kind of, doesn't seem brave in some sense. Anyone else? Yeah.
It's basically the same game as the 1-1-0-0 game in terms they're both Nash equilibria. But the payoffs aren't like the same scale. Yeah, you'd have to be really risk averse not to invest. So I thought people would be. So you invested? I invested, yeah. All right. So let me give this to Ali before I screw up the sound system here. OK, so we've got different answers out there. Can people hear each other's answers a bit? Yeah? So we have lots of different views out here. We have half the people investing and half the people not investing, roughly. And I think you can make arguments either way. All right? So we'll come back to whether it's exactly the same as the game we just saw. So the argument that, I'm sorry, your name is? That Patrick made is it looks a lot like the game we saw before. And we'll see it is related. Clearly, it's related in one sense, which we'll discuss now. So maybe I need this thing again. Where's this thing? Sorry. So what are the Nash equilibria in this game? What are the Nash equilibria in this game? All right, we can record someone's phone message, but in the meantime, what are the Nash equilibria in this game? Yeah, let me get the woman up here.
No one invests and everyone's happy that they didn't lose anything, or everyone invests and everyone's happy.
Good, good. So I've forgotten your name.
Kate.
So Kate's saying that there are two Nash equilibria, and with apologies to Jude, I'm going to put this on the board. All right, there are two Nash equilibria here. All right, one is all invest, and another one is no one invest. All right, these are both Nash equilibria in this game. Let's just check that they are, exactly the argument that Kate said, that if everyone invests, then no one would have any regrets. Everyone's best response would be to invest. And if nobody invests, then everyone would be happy not to have invested. That would be a best response. It's just in terms of what Patrick said, it is a game with two equilibria like the previous game, and that there are other similarities to the previous game, but it's a little bit of, the equilibria in this case are not quite the same as the other game. And the other game, that other equilibrium, the 0-0 equilibrium, seemed like a silly equilibrium. It isn't like we'd ever predicted happening. Whereas here, the equilibrium with nobody investing, right, actually is quite a plausible equilibrium. Right? If I think no one else is investing, then I strictly prefer not to invest. Is that right? Is that right? Okay. So two remarks about this. Do I want to do more before I do two remarks? Yeah, well, let's have one remark at least. How did we find those Nash equilibria? What was our sophisticated mathematical technique for finding the Nash equilibria in this game? So we should take. Can you get the mic on? Is it Kate? Kate, is that right? Yeah. So how did you find the Nash equilibria?
I looked for the only two places where there's no regrets.
All right. So in principle, you could have something. I mean, that works, but in principle, you could have looked at every possible combination, and there's lots of possible combinations. It could have been a combination where 1% invested and 99% didn't, and 2% invested and 98% didn't, and so on and so forth. Right? We could have checked rigorously what everyone's best response was in each case. But what do we actually end up doing in this game? What's the method? Yeah, we get the guy in. Yeah?
You only consider situations where your action can have a different outcome, and those only occur when everyone's investing or no one's investing.
That's true, so that certainly makes it easier. I claim, however, I mean, you're both of you being more rigorous and more mathematical than I'm tempted to be here. I think the easy method here, the easy sophisticated math here, is to guess. All right? My guess is the easy thing to do is just to guess what's likely to be an equilibrium here, and then what? And then check. All right? So a good method here in these games is to guess and check. And guess and check is really not a bad way to try and find Nash equilibria. The reason it's not a bad way is because checking is fairly easy. Right? Guessing is hard. You might miss something. There might be a Nash equilibrium hidden under a stone somewhere. Oh, no, it's not a stone. In America, it's a rock. It's hidden under a rock somewhere. All right? All right? But checking that something which you some putative equilibrium, some candidate equilibrium, checking whether it is an equilibrium is easy, because all you have to do is check that nobody wants to move away and everyone wants to deviate. Right? So I think in practice, that's what you're going to end up doing in this game. And it turns out to be very easy to guess and check, which is why you were able to find it. Right? So guess and check is a very useful method in these games where there are lots and lots of players, but not many strategies per player. It works pretty well. All right. Okay. Now, we've got this game up on the board. I want to spend a while discussing it because it's kind of important. So what I want to do now is I want to remind ourselves what happened just now. So what happened just now? Can we raise the yeses again? The invest again? And raise the not investors? Not invest? And I want to remind you guys you all owe me $10, all right? All right? And what I want to do is I want to play it again. Right? No communication. Write down again on the corner of your notepad what you're going to do. Don't communicate, you guys. All right, show your neighbor. All right, and now we're going to poll again. So, ready? Without cheating, without looking around you. If you invested, all right, let Jude get a good view of you. If you invested, raise your hand now. And if you didn't invest, okay. All right, can I look at the investors again? Just raise your hands, honestly. All right, we've got a few investors still. So these guys really owe me money now. That's good. All right, let's do it again. All right, third time. Third time. Hang on a second. So third time, write down. And pretend this is real cash. All right. Now, if you invested the third time, raise your hand. All right, we got it. All right, there's a few suckers born every day, but basically, all right. So where are we heading here? Where are we heading pretty rapidly? Right, we're heading towards an equilibrium. Right, just let's make sure let's confirm that. So everyone who didn't invest that third time, raise your hands. Right, that's pretty close. That show of hands is pretty close to a Nash equilibrium strategy. Is that right? Is that right? So here's an example of a third reason, something we already mentioned last time, but a third reason why we might be interested in Nash equilibria. There are certain circumstances in which play converges in a natural sense, not in a formal sense, but in a natural sense, to an equilibrium. Right? And we were, with the exception of a few dogged people who want to pay for my lunch, almost everyone else was converging to an equilibrium there. All right? So play converged fairly rapidly to the Nash equilibrium. All right? Well, we discussed there were two Nash equilibria in this game. Is one of these Nash equilibria, ignoring me for a second, is one of these Nash equilibria better than the other? Yeah, clearly the everyone investing Nash equilibrium is the better one. Is that right? Everyone agree? Everyone investing is a better Nash equilibrium for everyone in the class than everyone not investing. Is that correct? Is that correct? Nevertheless, where we were converging, in this case, was what? Where we were converging was the bad equilibrium. Right? We were converging rapidly to a very bad equilibrium, an equilibrium which no one gets anything, in which all that money is left on the table. Right? So how can that be? How do we converge to this bad equilibrium? To be a bit more formal, the bad equilibrium, the no-invest equilibrium here, is Pareto dominated by the good equilibrium. Everybody is strictly better off at the good equilibrium than at the bad equilibrium. It Pareto dominates, right? To use an expression that you probably learned in 150 or 115. All right? Nevertheless, we're going to the bad one. We're heading to the bad equilibrium. Why did we end up going to the bad equilibrium rather than the good equilibrium? Yeah, can we get the guy in gray? Yeah.
Well, it was a bit of a bear market for investors, wasn't it?
Just now, you mean it? All right. It's okay. So say what you mean a bit more. So yeah, that's good. So say a bit more.
So it seemed like people didn't have a lot of confidence that that other people were going to invest, and so it became a successively less desirable option to invest.
All right. So one way of saying that was when we started out, we were roughly even, roughly half-half, but that was already bad for the people who invested. All right, and then, so we started out at half-half, which was below that critical threshold of 90%, is that right? And from then on in, we just tumbled down. All right? So one way to say this, and one way to think about that, is it may matter, in this case, where we started. Right? Suppose the first time we'd played the game in this class this morning, suppose that 93% of the class had invested, in which case those 93% would all have made money. Right? Now, my guess is, I can't prove this, my guess is we might have converged the other way and converged up to the good equilibrium. Does that make sense? Yeah? So people figured out that people who didn't invest the first time, actually they played the best response to the class, so they stayed put, and those of you who did invest, a lot of you started not investing as you got caught up in this spiral downward, and we end up not investing. But had we started off above the critical threshold, the threshold here is 90%, and had you made money the first time around, then it would have been the non-investors that would have regretted their choice, and they might have switched into investing. And we might, I'm not saying we necessarily, but we might have gone the other way. Yeah, let me get a mic on.
What if it had been like a 30-70 thing where 70% invested?
Yeah, so that's a good question. So suppose we've been close to the threshold but below. So I don't know is the answer, obviously, because we didn't do the experiment, but it seems likely that the closer we got to the threshold, the better chance there would have been in going up. My guess is this is a guess, my guess is if we started below the threshold, we'd probably have come down, and if we started above the threshold, we'd probably have gone up. But that's not a theorem, I'm just speculating on what might have happened. I'm speculating on your speculations. All right, so here we have a game with two equilibria, one is good, one is bad. One is really quite bad, it's Pareto dominated. All right, and notice that what happened here, the way we spiral down, coincides with something we talked about Nash equilibrium already. It coincides with this idea of a self-fulfilling prediction. A self-fulfilling prediction. Provided you think other people are not going to invest, you're not going to invest. So it's a self-fulfilling prediction to take you down to not investing. Conversely, provided everyone thinks everyone else is going to invest, then you're going to go up to the good equilibrium. And I think corresponds to what the gentleman said in the middle about a bear market versus a bull market. Right? It was a bear market. It looked like everyone else didn't have confidence in everyone else investing, and then that was a self-fulfilling prophecy, and we ended up with no investment. All right? All right. Okay. Now, we've seen bad outcomes in the class before. For example, the very first day, we saw a prisoner's dilemma. Right? But I claim that though we're getting a bad outcome here in the class, this is not a prisoner's dilemma. Right? Why is this not a prisoner's dilemma? What's different between, both games have an equilibrium which is bad. Prisoner's dilemma has the bad equilibrium where nobody tidies their room or both guys go to jail. But I claim this is not a prisoner's dilemma. I'll get the guy two behind you. Yeah.
No one suffers, but no one gets any fun in this.
Okay, so maybe the outcome isn't quite so bad. That's fair enough. I could have made it worse, right? I could have made it sort of, I could have made that. I could have lowered the payoffs until they were pretty bad. Why else is this not a prisoner's dilemma? The woman who's behind you, Matthew.
Because there's no strictly dominant strategy.
Good, good. So in prisoner's dilemma, playing alpha was always a best response. What led us to the bad outcome in prisoner's dilemma was that alpha, the defect strategy, the non-cooperative strategy, the not helping tidy your room strategy, was always the best thing to do. Here, in some sense, the good thing, the moral thing in some sense, is to invest. But it's not the case that not investing dominates investing. In fact, if other people invest in the room, you want to invest. Is that right? Right? So this is a social problem, but it's not a social problem of the form of a prisoner's dilemma. All right? So what kind of problem is this? What kind of social problem is this? The guy in front of you.
Perhaps it's one of cooperation?
It's one of, okay, so it would help if people cooperated here, but I'm looking for a different term. A term that came up the first day. Coordination. This is a coordination game. For those people who read the New Yorker, I'll put an umlaut over the second O. It's a coordination game. Okay? All right. So why is it a coordination game? Because you'd like everyone in the class to coordinate their responses on invest. All right? And in fact, if they did that, then everyone would be happy. Right? And no one would have an incentive to defect. That would in fact be an equilibrium. But unfortunately, quite often we fail to have coordination. Either everyone, well, this is a form of coordination, either everyone plays not invest, or as happened the first time in the class, we get some split with people losing money. All right? So I claim that actually this is not a rare thing in society at all. There are lots of coordination problems in society. There are lots of things that look like coordination games, and often in coordination games, bad outcomes result. And I want to spend most of the rest of today talking about that because I think it's important, right? Whether you're an economist or whatever. So let's talk about it a bit. What else has the structure of a coordination game and therefore can have the outcome that people can be uncoordinated or can coordinate in the wrong place and you end up in a bad equilibrium? What else looks like that? Let's collect some ideas here. I've got a hand way at the back. Can you get the guy who's just way, way, way at the back, right up against the, yes, there you go. Great, thank you. Wait till the mic gets to you and then yell. Yeah.
Like a party on campus can be a coordination game.
Yeah, good, okay. So a party on campus is a coordination game because what? Because you have to coordinate at being at the same place. Is that right? That's the idea you had? Go ahead.
The thing is, like, if not very many people are coming, the people that did come are not going to enjoy it. But if a lot of people do come, then it will be good for everybody.
Good. Okay, that's good. So that's another way in which there's two ways in which a party can be a coordination problem. One is the problem that if people don't show up, it's a lousy party, so you don't want to show up. Conversely, if everyone's showing up, it's great, it's a lot of fun, it's the place to be, and everyone wants to show up. And second, so there's two equilibria there, showing up and everyone not showing up or everyone showing up. And similar idea, the location of parties, which is what I thought you were driving at, but it's the similar idea, can occur. So it used to be the case in New Haven that there were different, actually there aren't many anymore, but there used to be different bars around campus, none of which you're allowed to go to, so you don't know about. But anyway, lots of different bars around campus, and there's a coordination game where people coordinate on Friday night, or to be more honest, for graduate students, typically Thursday night. All right? So it used to be the case that one of those bars downtown was where the drama school people coordinated, and another one was where the economists coordinated, and it was pretty good equilibrium that they didn't coordinate at the same place. All right? All right? So one of the things you have to learn when you go to a new town is, where is the meeting point for the kind of party I want to go to? And again, you can have a failure of coordination, everyone's wandering around the town getting mugged. All right? All right? What other things look like coordination problems like that? So again, way back in the corner there, there's somebody right behind you. There you go. You have to really shout now.
Maybe warring parties in a civil war or signing a treaty.
Okay, that could be. So that could be a coordination problem. It has a feeling of being a bit prisoner's dilemma-ish. In some sense, my disarming, my putting down my arms before you putting down your arms, that kind of thing. So it could be a coordination problem, but it has a little bit of a flavor of both. Go ahead if you want. Okay. Other examples. There's a guy there. While you're there, why don't you get the guy behind you? There, by the door. There you go. Great.
At a sports arena, people deciding whether or not they want to start a chant for whatever team.
Yeah. Okay. I'm not quite sure which is the good outcome or the bad outcome. So there's this thing called the wave. There's this thing called the wave that Americans insist on doing, and I guess they think that's the good outcome. All right. Other things. Yeah, there's wait till I get to see you. Good.
Battle of the Sexes.
Let's come back to that one. Let's hold that thought, and we'll come back to it next time. You're right. That's a coordination one, but let's come back to it next time. All right. And anything else? Let me try and expand on some of these meeting place ideas. We talked about pubs to meet at or parties to meet at, but think about online sites. Online sites which are chat sites or dating sites or whatever. Right? Those online sites. Clearly have the same feature of a party. Right? You want people to coordinate on the same site. All right? Let me give some other. What about some other economic ideas? What about some other ideas from economics? What else has that kind of externality, like a meeting place? Can we get him, Patrick? Yeah?
I mean, it's excluding some people, but things like newspapers or something, like might want only one, like global news site.
All right, so that's an interesting thought, because it can go both ways. It could be a bad thing only to have one newspaper for obvious reasons, but in terms of having a good conversation about what was in the newspaper yesterday over lunch, it helps everyone's read the same thing. And certainly there's a bandwagon effect to this with TV shows. If everybody in America watches the same TV show, which apparently is American Idol these days, then you can all talk about it over lunch. Notice that's a really horrible place to coordinate. Right? There are similar examples to the American Idol example. When I was growing up in England, again, I'm going to reveal my age, everybody decided that to be an in-person in England, you had to wear flared trousers. Right? This was, and so to be in, you had to wear flared trousers. This is a horrible coordination problem, right? So for people who don't believe that could ever have happened in England, you could ever have these sort of fashion goods that you end up at a horrible equilibrium at the wrong place, you don't believe that could ever happen, think about the entirety of the Midwest. All right? I didn't say that. We're going to cut that off of the film later. All right? What else is like this? I'm getting a few ideas out. Let's get this gentleman here.
The establishment of monopolies, because a lot of people use Microsoft, then everything is compatible with Microsoft, so more people want to use it.
Good. So I've forgotten your name.
Stephen.
So Stephen's pointing out that certain software can act this way by being a network good. The more people who use Microsoft and Microsoft programs, the bigger the advantage to me using Microsoft. All right, and therefore, because I can exchange programs, I can exchange files if I'm working with my co-authors and so on, and so you can have different equilibria coordinating on different software, and again, you could end up at the wrong one. I think a lot of people would argue, but I'm going to stay neutral on this, a lot of people would argue that Microsoft wasn't necessarily the best place for the world to end up. All right? There are other technological network goods like this. These are called network externalities. An example here would be high-definition television. Right? You want to have one technological standard that everyone agrees on for things like high-definition televisions, because then everyone can produce TV to that standard and goods that go along with that standard. And of course, it matters. Each company who's producing a TV and has a standard in mind would like theirs to be chosen as the standard. And again, you could end up at the wrong place. You could end up at a bad equilibrium there. All right. How about political bandwagons? Right? In politics, particularly in primaries, there may be an advantage on the Democratic side or on the Republican side in having you all vote for the same candidate in the primary, so they get this big boost and it doesn't seem like your party's split and so on. Right? And that could end up, and again I'm going to remain neutral on this, it just could end up with the wrong candidate winning. Right? There's a political bandwagon effect. The person who wins New Hampshire and Iowa tends then to win everything. All right? All right? So that's another example. Any other economic examples? Yeah, can we get this guy in here?
Listing on a stock exchange?
Yeah, okay, so in particular, which stock exchange to list on, right? So there's a huge advantage in having lots of stocks on the same stock exchange. There are shared fixed costs. There's also liquidity issues, all right, and lots of issues of that form, mostly of the form of fixed costs. So there's a tendency to end up with one stock exchange. We're not there yet, but we do seem to be going that way quite rapidly. Right? The problem, of course, being that might not be the best stock exchange, or it might give that stock exchange monopoly power. All right? Let me throw out one more example. What about bank runs? What's a bank run? What's a bank run? Somebody? Yeah, can we get this guy? What's a bank run?
It's when
shout out. Yeah.
When the public loses confidence in their security of their money in banks, then they rush to withdraw the deposits.
Good. So you imagine a bank as a natural case where there's two equilibria. There's a good equilibrium. Everyone has confidence in the bank. Everyone leaves their deposits in the bank. The bank is then able to lend some of that money out and earn a higher rate of interest on it. The bank doesn't want to keep all that money locked up in the vault. It wants to be able to lend it out to lenders who can pay interest. Right? That's a good equilibrium for everybody. However, if people lose confidence in the bank and start drawing their deposits out, then the bank hasn't got enough cash in its vault to cover those deposits, and the bank goes under. All right? Now, I used to say at this point in the class, none of you will ever have seen a bank run because they stopped happening in America more or less around in the mid-30s. There were lots and lots of bank runs in America before the 1930s, but since federal deposit insurance came in, there's far fewer. However, I really can't say that today because there's a bank run going on right now. Right? There's a bank run going on actually in England with a company called Northern Rock it's called, Northern Rock, as we speak. Right? And it really is a bank run. I mean, if you looked at the newspaper yesterday on the New York Times, you'll see a line of depositors lined up outside the offices in London of this bank trying to get their deposits out, and you see the Bank of England trying to intervene to restore confidence. And just to be clear, this isn't a simple case of being about the mortgage crisis. This bank does do mortgages, but it doesn't seem to be particularly involved in the kind of mortgages that have been attracting all the publicity. It really seems to be a shift in confidence, a move from the good equilibrium of everyone remaining invested to the bad equilibrium of everyone taking their money out. Hang on a second. Okay. Now, there are famous bank runs in American culture. In the movies, anyway. What is the famous bank run in the movies, in American movies? It's a Wonderful Life, all right? There's one in Mary Poppins as well, but we'll do It's a Wonderful Life. How many of you have seen It's a Wonderful Life? How many of you have not seen It's a Wonderful Life? Can you get a poll here? How many people have not seen it? Keep your hands up a second. Keep your hands up. You need to know that if you're on a green card, you can lose your green card if you haven't seen It's a Wonderful Life, okay? All right? So in It's a Wonderful Life, there's a run on the bank. Actually, it's a saving and loan, but never mind. We'll think of it as a bank. All right? And luckily, it doesn't end up with the saving and loan or bank going under. Why doesn't the bank go under in It's a Wonderful Life? Why doesn't it go under? Yeah, the guy in green. Can we get the guy in green? Yeah.
Everyone agrees to only take as much as they need and not to take out their entire deposit.
All right, so if people didn't hear it, everyone agrees only to take out a small amount, perhaps even nothing, and therefore the bank run ends, everyone realizes the bank isn't going to collapse, and they're happy to leave their money in the bank. Now, it's true everyone agrees, but why do they agree? What makes them agree? What makes them agree is Jimmy Stewart, right? right? Everyone remember the movie, right? So Jimmy Stewart gets up there and he gives a speech, and he says, look, more or less, I mean, he doesn't say it in these words, but he would have done if he'd taken the class. He says, look, there are two equilibria in this game. I can't do the, whatever it is, West Pennsylvania accent, whatever it is. Is that where it's from? Anyway, but there are two equilibria in this game. There's a bad one where we all draw our money out and we all lose our homes eventually. And there's a good one where we all leave our money in, and that's better for everyone, so let's all leave our money in. Right? But he gives this, he's a bit more motivationally stimulating than me, right? But he leads to people not leaving their money in. So what I want to do is, I want to pick on somebody in the class now. Everyone understands this game. Everyone understands there's two equilibria. Everyone understands that one equilibrium's better. Let's play the game again. Let's choose the game again. But before I do, I'm going to give the mic to Patrick here. And Patrick is going to have exactly 5 seconds to persuade you. Stand up, stand up, stand up, stand up. Patrick's going to have 5 seconds to persuade you, well, whatever he likes. He can do whatever he likes, starting now.
Okay, so clearly if we all invest, we'll all be better off. So everyone should invest.
All right, all right. Now, let's see if this is going to work. Let's have a round of applause, Patrick. Okay. So let's see what happens now. Everybody, oh, we haven't got time to write it down. Everyone who's going to invest, raise their hands. Everyone's going to invest, raise their hands. And everyone who's not investing, raise their hands. Oh, we almost made it. We must have almost made it. All right? So notice what happened here. Let's give another round of applause for Patrick. I think he did a good job there. But there's a lesson here. Right? The lesson here is the game didn't change. It's the same game that we've played 3 times already. This was the 4th time we played it. We had a totally different response in playing this time, right? Right? Almost all of you, the vast majority of you, perhaps even 90% of you, invested this time. Right? And you did so in response to Patrick, but Patrick wasn't putting any money down, he wasn't bribing you, he wasn't writing a contract with you, he wasn't threatening to break your legs, he just was pointing out it's a good idea. Right? Now remember the prisoner's dilemma. In the prisoner's dilemma, if Patrick could have got up in the prisoner's dilemma and given the same speech and said, look guys, we're all better off if we choose beta in the prisoner's dilemma than if we choose alpha. Right? Roughly the same speech. And what would you have done in the prisoner's dilemma? You'd have all chosen alpha anyway. Right? So Patrick trying to persuade you, or Patrick communicating to you that you do better by choosing beta in the prisoner's dilemma doesn't work. But here, don't go yet, here it does work. Why is Patrick persuasive in this game, but he isn't persuasive in the prisoner's dilemma? Yeah, can we get the mic on Katie again? Yeah. Why is Patrick persuasive in this game and not before?
He's not trying to persuade us to play a strictly dominated strategy.
He's not trying to get you to play a strictly dominated strategy, and more than that, he's trying to persuade you to play what? To play a Nash equilibrium. All right? So there's a lesson here in coordination problems. Unlike prisoner's dilemma, communication, just communication, no contract, communication can help. And in particular, what we can persuade each other to do is to play the other Nash equilibrium. And this gives us one more motivation for a Nash equilibrium. In a prisoner's dilemma, to get out of it, we needed a contract. We needed side payments. We needed to change the payoffs of the game. But a Nash equilibrium can be a self-enforcing agreement. The Nash equilibrium can be self-enforcing agreements. We can agree that we're going to play invest in this game, and indeed we will play invest without any side payments, without anybody threatening to break your leg, without any contracts, without any regulation or the law. I'm assuming Patrick isn't that violent. All right? We're going to end up doing the right thing here because it's in our own interest to do so. All right? All right, so coordination problems, which we've agreed are all over society, whether it comes to bank runs or bubbles, we haven't talked about that, bubbles in the market, or fashion in the Midwest, they're all over society. Communication can make a difference. And we'll pick that theme up on Monday. It's going to be used in lots of applications, it's going to be used in your McKinsey interview. That's not a very good reason, right? And I certainly don't want you to jump to the conclusion that now we've got to Nash equilibrium, everything we've done up to now is somehow, in some sense, irrelevant. That's not the case. It's not always going to be the case that people always play a Nash equilibrium. For example, when we played the numbers game, the game when you chose a number, we've already discussed last week, or last time, that the equilibrium in that game is for everyone to choose 1. But when we actually played the game, the average was much higher than that. The average was about 13. It is true that when we played it repeatedly, it seemed to converge towards 1, but the play of the game when we played it just one shot, first time, wasn't a Nash equilibrium. All right? So we shouldn't fall into the mistake of thinking people always play Nash equilibrium, or people, if they're rational, play Nash equilibrium. Neither of those statements are true. Nevertheless, there are some good reasons for thinking about Nash equilibrium, other than the fact it's used by other people, and let's talk about those a bit. So I want to put down some motivations here. All right, the first motivation we already discussed last time. In fact, somebody in the audience mentioned it, and it's the idea of no regrets. So what is this idea? It says, suppose we're looking at a Nash equilibrium. If we hold the strategies of everyone else fixed, no individual I has an incentive to deviate, to move away. All right, so again, holding everyone else's actions fixed, no individual has any incentive to move away. And let me be a little bit more careful here. No individual has any strict incentive to move away. All right, we'll see that that actually matters. Right, so no individual can do strictly better by moving away. All right? No individual can do strictly better by deviating. Okay, so last time we came across a new idea, although it wasn't really new for a lot of you, and that was the idea of Nash equilibrium. And what I want to do today is discuss Nash equilibrium, see how we find Nash equilibrium in some rather simple examples, and then in the second half of today, I want to look at an application where we actually have some fun and play a game, at least I hope it's fun. All right, but let's start by putting down a formal definition. We only used a rather informal one last week, so here's a formal one. A strategy profile, remember a profile is one strategy for each player, so it's going to be S1 star, S2 star, all the way up to Sn star if there are n players playing the game. So this profile is a Nash equilibrium, and I'm just going to write Ne in this class for Nash equilibrium from now on. If for each I, so for each player I, her choice, so her choice here is Si star, that's I is part of that profile, is a best response, to the other player's choices, And of course, the other player's choices here are S minus I star. So everyone is playing a best response to everyone else. All right? Now, this is by far the most commonly used solution concept in game theory. So those of you who are interviewing for McKinsey or something, you're going to find that they're going to expect you to know what this is. All right? So one reason for knowing what it is because it's in the textbooks, was my best response. And notice that wouldn't be true at some other outcome. So for example, if player 1 had chosen S1 star, but player 2 had chosen some other strategy, let's say S2 prime, then player 1 would have regrets. Right? Player 1 would wake up the next morning and say, oh, I thought player 1 was going to play S2 star. In fact, she chose S2 prime. I regret having chosen S1 star. I would have rather chosen S1 prime. Right? So only at the Nash equilibrium are there no regrets. All right? Everyone okay with that? This is just revisiting really what we did last time and underlining these points. All right. So I want to spend quite a lot of time today just getting used to the idea of Nash equilibrium and trying to find Nash equilibrium. I'm going to turn off that projector that's in the way there, if I can. Okay. Is that going to upset the lights a lot? All right. So, okay. So what I want to do is I want to look at some very simple games with a small number of players to start with and a small number of strategies, and I want us to get used to how we would find the Nash equilibria in those simple games. Okay? We'll start slowly, and then we'll get a little faster. Okay, So let's start with this game. Very simple game with 2 players. Each player has 3 strategies. And I'm not going to motivate this game. It's just some random game. Player 1 can choose up, middle, or down. And player 2 can choose left, center, and right. And the payoffs are as follows: 0, 4, 4, 0, 5, 3, 4, 0, 0, 4, 5, 3 again, 3, 5, 3, 5, and 6, 6. All right? So we could discuss, if we had more time, we could actually play this game, but it isn't a particularly exciting game. To remind ourselves how that arose in the example we looked at the end last time. I'm not going to go back and reanalyze it, but I just want to sort of make sure that we followed it. So we had this picture last time in the partnership game in which people were choosing effort levels. And this line was the best response for player 1 as a function of player 2's choice, and this line was the best response of player 2 as a function of player 1's choice. All right, this was the picture we saw last time. And let's just look at how those, it's no secret here what the Nash equilibrium is. The Nash equilibrium is where the lines cross, but let's just see how it maps up to those 2 motivations we just said. So how about self-fulfilling beliefs? Well, if player, sorry, I've put a 1, that should be 2. If player 1 believes that player 2 is going to choose this strategy, then player 1 should choose this strategy. If player 1 thinks player 2 is choosing this strategy, then player 1 should choose this strategy. If player 1 thinks player 2 is choosing this strategy, then player 1 should choose this strategy, and so on. That's what it means to be a best response. But if player 1 thinks that player 2 is playing exactly her Nash strategy, then player 1's best response is to respond by playing his Nash strategy. And conversely, if player 2 thinks player 1 is playing his Nash strategy, then player 2's best response, indeed, is to play her Nash strategy. All right, so you can see that's a self-fulfilling belief. If both people think that's what's going to happen, that is indeed what's going to happen. All right, how about the idea of no regrets? So here's player 1, she wakes up the next morning, or sorry, it was he, wasn't it? He wakes up the next morning and he says, I chose S1 star, do I regret this? Well, now he knows what player 2 chose S2 star, and he says, no, that's the best I could have done. Given that player 2 did in fact choose S2 star, I have no regrets about choosing S1 star, that in fact eating, comma, holding everyone else fixed. All right? So why do I call that no regret? It means having played the game, suppose you did in fact play a Nash equilibrium, and then you look back at what you've done, and now you know what everyone else has done, and you say, do I regret my actions? And the answer is, no, I don't regret my actions, because I did the best I could given what they did. All right? So that seems like a fairly important sort of central idea for why we should care about Nash equilibrium. Here's a second idea, and we'll see others arise in the course of today. The second idea is that a Nash equilibrium can be thought of as self-fulfilling beliefs. So in the last week or so, we've talked a fair amount about beliefs. If I believe the goalkeeper is going to dive this way, I should shoot that way, and so on. All right? But of course, we didn't talk about any beliefs in particular. These beliefs, if I believe that, if everyone in the game believes that everyone else is going to play their part of a particular Nash equilibrium, then everyone will in fact play their part of that Nash equilibrium. All right? Now why? Why? Why is it the case that if everyone believes that everyone else is playing their part of this particular Nash equilibrium, that that's self-fulfilling and people actually will play that way? Why is that the case? Anybody? Yeah, can we get this guy in red? Yep.
Because your own Nash equilibrium strategy is a best response against those.
Exactly, exactly. So it's almost a repeat of the first thing. If I think everyone else is going to play their particular, if I think players 2 through n are going to play S2 star through Sn star, then by definition, my best response is to play S1 star, so I will in fact play my part of the Nash equilibrium. All right, good. Good. All right. So as part of the definition, we can see these are self-fulfilling beliefs. Let's just